Elect 377 Operating Systems. The stack buffer layout. As we mentioned in the previous presentation on global overflow attacks, the buffer or array overflow is one of the most common exploit attacks, and it exploits a bug as a security hole. Some languages such as C and C++ do not check array bounds. Some library routines such as getC and strcpy also do not check array bounds. There are three variants of this attack based on the array. The previous presentation talked about attacks on global buffers and global arrays. This presentation and the next presentation will talk about attacks that use the stack, buffers that occur on the stack. And the last presentation will talk about attacks on the heap. The key concept behind all of these is that memory after the array contains other entities such as global variables, return addresses, and heap pointers that can be corrupted during an attack. The stack overflow is one of the most common. We write binary code into a buffer ending with a value that overwrites the return address and points to the buffer. When the subroutine returns, it uses that return address and returns into the stack and executes on the code on the stack instead of returning to the calling program. One of the protections is that we don't allow the stack space to be executable. But not all architectures support making the stack non-executable. One other approach is not to put buffers on the stack, but as we've already seen, global variables that are buffers and heap buffers that we will see in a future presentation may also be vulnerable. So before we can understand the mechanisms of the attack itself, we first have to understand the architecture of subroutine call and return. There are two general approaches. The approach on the Intel architecture, both the 32-bit and the 64-bit architecture, on the PowerPC and on ZOS, is that when you call a subroutine, the return address is pushed on the stack. This is still the most common server architecture, so we'll use these as an example. On the ARM architecture and on NEOS, the return address is stored in a link register. If you don't call any other functions, the return address stays in the link register and nothing really happens. However, if you call any other functions from within that function, that other call will also use the link register, so you have to save it on the stack. And when you save it on the stack, it is still vulnerable. Even if you don't save it to the stack, if you save it to some global memory location, as we've just seen, global memory locations are also vulnerable. So the purpose of this presentation is to understand the layout of the stack before we discuss how the layout of the stack can be exploited to make an attack. Let's look at what happens when we call a library function such as fopen. Now, the particular example we're using is from the 32-bit Intel architecture such as used on a Pentium. The 64-bit Intel architecture is similar. The only difference is that instead of 4 bytes for a pointer, we use 8 bytes for a pointer. But the registers and the layout of the stack are very similar. So when we call fopen, there are three parts to this. We push the parameters, we call the function, and then we restore the stack from the call. So the first thing that we do is we push the parameters in reverse order. The contents of those strings, fopen, the file, and R, these are actually content strings. Like we could say fopen test.dat and quote R. The actual strings are constant strings in the program source and are stored in a global data segment, but we push the pointers to those strings on the stack. We push them in reverse order because some of the function calls in the C language allow variable number of parameters. For example, printf. The first argument to printf is the format string. And the number of percent operations in the format string tell you how many parameters there are in that call to printf. So the one on the top of the stack, which is the easiest one to find, has to be the first parameter. In fopen, there is only ever two parameters, but the convention in C is that we push them in reverse order so that it is easier to implement calls like printf. So we push the pointer to the string R on the stack, and then we push the pointer to string 1 on the stack. When we call fopen, this will push the return address on the stack. Inside of fopen, we will push the base pointer, and the base pointer is used to access both parameters and local variables inside of a function. After that, we move the stack pointer to the base pointer, and we subtract the number of bytes in the local variables from the stack pointer. So now you can see we have two stack frames on the stack now. At the bottom of the stack frame where the stack pointer is, we have the local variables. In the middle of the stack frame, we have the saved base pointer and the return address. The base pointer points to the saved base pointer, and the saved base pointer points to the middle of the previous stack frame. And above the return address, we have the parameters. So if you follow the saved base pointer up, you will see the previous stack frame with a local variable. There's one local variable of 4 bytes long, which is FD. We have the saved base pointer and the return address and any parameters that were made to that function. And that saved base pointer points to the previous stack frame all the way up to the main function. After we have moved the stack pointer down by subtracting the number of bytes in the local variables from the stack pointer, we do whatever happens inside of fopen, which in this case is most likely a call to the system call open, allocating a file data structure, allocating buffers, and returning a pointer. The return value goes in the EAX register. So at the end, when we hit the end of the fopen register, when we hit the end of the fopen function, the return value should be in the A register, and when we execute the leave instruction. The leave instruction does two things. The first thing it does is it moves the stack pointer to the base pointer, which frees up all of the local variables off of the stack. And then it pops the saved base pointer into the base pointer, moving the base pointer back up to the previous stack frame. At which point in time, the stack pointer is now pointing to the return address, in which case the return instruction returns us to the calling location. The calling location moves the A register into the local variable. The local variable FD is accessed by 4 bytes below the base pointer. Local variables are accessed by subtracting the offset off of the base pointer. Parameters are accessed by adding the offset onto the base pointer. We then add 8 to the stack pointer to remove the parameters that we had pushed on the stack. And at this point in time, the call to fopen is done. Let's take a look at what happens when we call the library function that wraps the system call open. So we are starting from a very similar stack frame. We have the parameters to the current function, the return address from where the current function is called from, the saved base pointer that points to the previous stack frame, and our base pointer points to this location, and the variable FD, which is a 4-byte variable that is just below the base pointer, with the stack pointer pointing to the current limit of the stack. So again, we push the parameters in reverse order. We push 0744, which is an octal string. We push the flags O read only. Both of these are 4-byte values, and then we push the pointer to the string, the file. We then call open, which pushes the return address and enters open. Open also pushes the base pointer to create a minimal stack frame and moves the base pointer down there to make it easy to access the parameters. We don't allocate any local variables because this is a simple wrapper to a system call, so it doesn't need any local variables. The system call uses registers to communicate with the kernel instead of the stack. So instead of pushing the parameters to open, we instead move the system call number, open as system call 5, to the A register, and we put the parameters in the B, C, and D register. The A register contains the number of the system call. The open function is system call number 5, so we move the value 5 into the A register. The parameters to the system call are stored in the B, C, and D registers. So we move the first parameter, which is at the top of the parameters on the stack, which is the address closest to the base pointer, 8 bytes away from the base pointer, is moved to the B register, which contains a pointer to the name of the file. 12 bytes away from the base pointer is moved into the C register, which is the second parameter to open, which is the O read-only. And 16 bytes away from the B register is moved into the D register, which is the flag containing the permissions of the file if the file had to be created. We then do the trap instruction, which on the Intel is called int for a software interrupt, and that makes a system call and stores the return address on the kernel stack and does whatever a trap does inside of the kernel, which is look into the system call table for location 5 and do whatever is needed to do to open a file. When it returns, the return value from a system call is in the register A, EAX. Since the register A is also what we use at the user level to return a value from a function call, we don't have to do anything. The return value is already in the A register, so we pop the base pointer and return, which takes us back to the location where we called open from. We then move the A register into the variable, which is done by subtracting the offset from the base pointer, and then we add 12, which is 3 parameters of 4 bytes each, to the stack pointer to pop all of the parameters off the stack, and the call to open is finished. The next presentation will discuss how we use this stack layout in order to make an attack on a program. This is the end of the stack layout presentation.